Hello, everyone. My name is Amy Brown. I'm the Director of Events and Education for Trade Press Media Group and Facilities Net. Thank you for joining us for today's webcast, Optimizing Chilled Water Plants for Energy Savings. Our presenter today is Edmundo Camille, Product Manager for Carrier Systems. Ed has over 30 years of expertise in the HVAC industry. He has a background in mechanical engineering, with experience in product application, service engineering, international sales, and HVAC systems design. Ed has been a Carrier employee for 20 years, leading sales and engineering in international markets and North American service engineering. Before we begin, just a few pieces of information. Today's webcast learning objectives include discussing the advantages and disadvantages of chilled water systems. Learn about the difference between IPLV, NPLV, and SPLV. Understand energy savings opportunities from the operation standpoint, and identify areas of opportunities for retrofit implementation. Before we get started, just a few other details. A live question and answer session will follow today's presentation. To submit your questions, please navigate to the Q&A button at the bottom of your screen and type in your question. We'll answer as many questions as time permits. At the conclusion of today's webcast, you'll receive a PDF copy of today's slides. You'll also receive a link to a brief online assessment. And upon successful completion of this assessment, you'll receive a CEU certification that you can use to apply to any organization or designation that you own. And then today's webcast will also be archived at facilitiesnet.com/webcast. And with that, I'll turn it over to you, Ed.
Thank you, Amy. Thank you so much for the presentation about myself. And thank you, everyone, for joining today's webinar about optimizing chiller plant for energy savings. This is the learning objectives. This is today's agenda. And although Amy did a great job already introducing the four main topics for today's, I just want to mention that the main objective of this webinar is to present ideas and key points to consider when chilled water systems are evaluated for optimization. It is not really the intent to tell you what to do, but rather what to think about when you deal with these types of analysis. Myself and Carrier members in my group and the entire organization are here to provide the support that all of you need, the HVAC community. So by all means, feel free to connect with us if you need any help. The first point, we're going to review the main chilled water systems that we usually encounter in the field, and we will highlight the main differences between them. Then we are going to spend time reviewing some energy efficiency indicators, which simply put are single numbers that are calculated following a specific method described in the Air Conditioning, Heating, and Refrigeration Institute Standard 550 and 590. And this is important in this discussion, just to remind ourselves that we have different ways to calculate efficiency values, but one calculation in a specific is about the system efficiency. The third section, energy savings opportunity from operation, is when we will present areas of improvement from the operational and technical standpoint. Most likely you will hear me saying things that are not new by any of you, but what happens is that sometimes we tend to forget some of these basic foundations or concepts. And lastly, retrofits, areas of implementation. We're going to discuss areas to consider or how to map the process of any energy efficiency improvement. Okay, so the first topic, the chilled water system, started with this one. And for the most part, we're going to concentrate on closed systems. We can divide this in two, constant flow and variable flow. And then a subdivision of this from the installation standpoint. It could be either series arrangement or parallel configuration or arrangement, which are applicable to both type of chillers, air-cooled and water-cooled. For constant flow, and generally speaking, which is the first bullet point that you see on the slide, the common configuration is parallel arrangement. What is going to drive whether it's one or the other is basically the system requirements. For example, a high chiller water delta T, let's say 12 degrees or 14 degrees or even 16 degrees sometimes, it will require, for the most part, to be a serious installation. We can, however, find installations where the chillers are installed in parallel arrangement and the delta T across the coolers is high. So although series arrangement or configuration is more conducive or appropriate for a high delta T application, it does not necessarily mean that it's always the case. Now, if the total capacity and water flow rate are divided into the number of units available, let's say 2 chillers, 3 chillers, or 4 chillers, then we will be talking about parallel configuration. For example, a building of 500-ton nominal capacity with 2 chillers in parallel means that each chiller will provide 250 ton at their respective flow rate, which is a function of the delta T across each cooler. As for the primary and secondary, we usually talk about constant primary and variable secondary. The whole hydronic system is divided in 2 sections, and each section has its own set of water pump. There is also a valid application where both primary and secondary flows or loops rates are available. And in the next slide, we're gonna talk more about primary and secondary, some advantages and disadvantages of this system as well as others. Then we have the VPF, also known as variable primary flow, which for the most part is applied on the chiller water circuit. You will also see applications where the condenser water flow varies as well, but these type of applications are critical. And to consider variable flow in the condenser, we really need to understand the limitations, not only about the equipment, not only the limitations on the equipment, but also about the system as a whole. And these limitations are the ones which allow us to decide and determine what can be done and how. An important point that is not in this slide, but I do believe that it's important to mention, is that from the pumping type standpoint, we can mention 2 types, either manifold or dedicated pumping. Dedicated pumping is when each chiller has its own water pump and can be applied to the chiller water or condenser water loops, or both at the same time. Sometimes we see this type of pumping when different chillers capacities are installed, and we call this type of system asymmetrical. So different capacities lead to different flow rates and therefore different water pressure drops. And this is just one application among many others that we can find in the field. Manifolded pumping is when the pumps discharge fluid to a header, and then from this header, water is supplied to the building. And in this type of pumping structure or configuration is usually applied to increase redundancy and also flexibility. And once again, this is a very high level introduction about chill water systems and closed systems in particular. Continuing with chill water systems, this is a rough summary, a rough table of the main 3 that we see, I would say, every day. We know that from the application standpoint, we can number so many other types, but in today's webcast, we're going to concentrate in these 3, constant primary and secondary, and variable primary. Constant primary flow can be applied to a single chiller or multiple units, not only in the chill water circuit, but also in the condenser side as well. It's a very simple system to implement. This is usually 2 pipe for cooling, 4 pipe for cooling and heating, in addition to, of course, the condenser water in the case of water-cooled chillers. One of the issues with constant flow is the low delta T partial load. And it is a big issue, especially on comfort cooling, due to the fundamental load profile. Primary and secondary, very common and very old concept. In these systems, we find 2 sets of chill water pumps, as I mentioned in the last slide. One set of pumps in the constant flow loop, which essentially is where the chillers are located. Some engineers call this production loop the production loop because it's where the chillers provide chill water temperature. And the second set of pumps is located in the variable flow loop, and that's where the load is located. In other words, the building itself or the application itself. In between these loops, there is a bridge, also called hydraulic decoupler, and it is used to balance the thermal energy between the primary and secondary loops. The water can flow in either direction within the bridge from primary to secondary and vice versa. And this depends on which flow is greater at any given point in time and depending upon the load of the building. The intent with this system is to isolate the control of the chillers from the coils. And one of the biggest disadvantages with this PS primary and secondary system is the capacity matching between the loops, regardless the bridge or the coupler, and that basically leads to a low delta T problem. I'm sure that all of you are very familiar with the sick building effect or the low delta T syndrome, causing all kinds of problems concerning temperature control and energy balance. Then for variable primary, it's essentially a primary and secondary system, but without one set of pumps. This system basically eliminates the set of pumps in the primary loop, but the secondary pumps remain. In this type of systems, the flow varies through the chillers, through the coils, and throughout the building. And the main idea, the whole idea is to save energy by varying the flow using BFD. That's a very general and main concept about BPF or variable primary flow. One of the disadvantages of the BPF at some extent is the controls implementation and how well and efficient the system is being handled, especially at partial load and during stacking. We have, here in Carrier, we have implemented a set of rules from the control system point that relies on three main key design elements or parameters. Number one is water velocity. It shouldn't fall between 3 feet per second, 2.5 feet per second. Below this velocity, is either 3 or 2.5, is the flow is considered to be laminar, and the heat transfer effect is diminished, affecting the chiller's performance and, most importantly, the stability. And number two point to consider is the flow change rate that must not exceed approximately 30% of the design flow rate. And number three is the flow variation that has to be linear and proportional with the load. It sounds redundancy because if it's linear, it's definitely and by definition proportional. So in other words, if the load drops 10%, then the flow must be reduced by 10% and vice versa. If the load increases by 10%, then the flow must be increased by 10%. So moving on with topic number two of the learning objective, differences between IPLV and NPLV, and SPLV. So some of you might recall that back in late 1990s, ARI published a new standard that basically affects the rating and testing of chillers used in comfort cooling. This standard, which is the one that I'm sure that you all know, is the 550 and 590 standard. And this one replaced two individual standards, the 550 1992, basically for centrifugal and screw chillers, and the 590 1992 for chillers using positive displacement compressors. The objective at the time, back in the 90s, late 90s, was to minimize the confusion and also bring some sort of consistency between the 550 and 590. So ARI decided that by combining these two into a major one would help the HVAC industry to have a better understanding of this standard. The standard defines key terms and rating conditions that affect the chillers and the chillers only, and it does not take in consideration any other equipment in the system but the chillers. Again, just the chillers. Several things changed at the time when they implemented or combined these two, the 550 and 590 into one. The weighted average of operating time and the par load points based on ton hours rather than just hours. That's one of them. Fouling factor was another one, another key factor that was changed or modified, if you will. It was reduced from 0.00025 to 0.0001. And this provided actually a positive effect, which was that equipment owners can purchase by the capacity that they actually need without incurring in more capacity just because the extra resistance that was imposed by the higher fouling factor in the evaporator. ARI established two main figures for power load efficiency ratings, which is a single number, again, about the standalone chiller performance. This number is a weighted average number based on a specific criteria of calculation. And these two efficiency ratings are the IPLV and the NPLV. The IPLV stands for integrated power load value, and the NPLV stands for non-standard power load value. As we can see in the slide from left to right, if we start from left to right, the IPLV is being calculated based on a predetermined conditions that has already established by this institute, like the AHRI. And these conditions are flow rate, chill water temperature, condenser temperatures at different capacity points. Right in the middle, in the NPLV, once again, non-standard power load value, and this one is calculated based on conditions relevant to the site. But like the IPLV, once again, is for a standalone or single chiller. Notice that the IPLV box on your left, or that section includes an equation which is valid for both IPLV and NPLV. And we're going to talk more about this, especially the numbers on the denominators, and as well as the letters in the next slide. Keep in mind, once again, the IPLV and NPLV are metrics for a single chiller. And if we take in consideration that energy consumption is a function of building type, load profile, weather conditions, chillers, type of chillers, whether it's constant speed or variable speed, chill water pumps, condenser water pumps, we can basically conclude that the IPLV nor the NPLV are good enough to define a comprehensive energy efficiency or energy analysis about the system. And that's the reason why we bring the last box on your right, the SPLV. The SPLV stands for System Power Load Value, and it was introduced by Carrier using the same idea or concept from the AHRI 550-590. This is the energy analysis that I was referring to before when I was mentioned that not IPLV nor NPLV are good enough to provide a really good comprehensive energy analysis of the system. The SPLV provides a way much better picture about the system's efficiency and energy consumptions, because it is calculated considering everything in the system, not only the chillers, but the pumping power, cooling tower, type of hydronic system, whether it's constant flow, VPF, primary and secondary load profile, and definitely climate conditions. So think about this, climate conditions. The energy consumption of a system, including 3 500-ton chillers with dedicated pumping running under primary and secondary configuration in Syracuse, New York, is going to be completely different if we install the same system, the same chillers, the same configurations down in the Southeast here in Miami area. And this is important because when retrofits or optimizations are being considered, we need to model the system before and after, so we provide a better and a comprehensive analysis about energy consumption of the system and not just about the chillers. And then, of course, we can translate this, all these numbers, this overall energy indicator or value into a financial language or terms, whether it is payback, net present value, ROI, return on investment, or whatever we need. Okay, moving on power load values. Notice in this table that rating conditions for both IPLV and NPLV are indicated. From left to right, the first column indicates the specific conditions for each product or chiller type. The living chill water temperature, which is the first block in the middle column, is 44 degrees, and it is constant for all type of chillers if we are calculating the IPLV. Now, if you move to the right under the NPLV, you will notice that the living chill water temperature is not 44. It's blank, and it's basically because it's as specified. For example, it could be 45 degrees, it could be 42, it can be 44, or it can be actually the same 44 as the IPLV states. And if we keep going down in this column, in the first one in particular, we see a specific condenser entering temperatures depending upon the condenser type, whether it's water cool, air cool, etc. And those temperatures correspond to a specific load points, such as 100% load, 75%, 50, and 25%. To calculate or compute both IPLV and NPLV values, we need to know the efficiency of the unit in either kW per ton, COP, coefficient of performance, or EER, energy efficiency rating, of those 4 points, I'm sorry. Again, 100%, 75, 50, and 25%, and at their respective entering condenser water or air temperature, whether we're dealing with a water-cooled chiller or an air-cooled chiller. And these values are represented by the letters A, B, and C, and D that we're seeing on the denominator in that equation. So these numbers that we see, like 0.01, 0.42, etc., they represent the percentage of time that the unit operates under that specific load. For example, A alpha represents the load, 100% capacity, and 0.01 indicates that the unit operates 1% of the time under 100% load. B beta represents the load of 75%, or the kW per ton at 75%, and 0.42 indicates that the unit operates 42% of the time at 75% capacity. And the same concept applies for letters C, Charlie, and Delta, 45% and 12% respectively. Two important pieces of information here is one, the fouling factor for cooler and condenser is specified to be 0.0001 and 0.00025, and also the flow rate for both condenser and evaporator has been specified as 3 GPM per ton for the condenser and 2.4 GPM per ton for the cooler. So once again, if a water-cooled chiller is to run at other than those conditions, I mean, other than ARI, this 550, 590 standard or under IPLV, then it is considered to be running at non-standard values. In other words, this NPLV, which once again stands for non-standard part load value, is calculated based upon a specific site conditions. So as I mentioned in the previous slide, and once again, the IPLV and NPLV are based on single chiller calculation for standalone chillers. We all know that 80% or more chilled water plants usually have multiple chillers. So these efficiency values do not precisely represent plant operating conditions. So in other words, to determine the true efficiency or energy consumption of a chilled water plant, we really and truly must perform full energy analysis by implementing the SPLV or the system part load value, as I mentioned in the previous slide. And this is basically the main takeaway or message in this from this slide. So moving on to topic number 3, energy savings opportunities from operation. Our friends from ASHRAE states that HVAC systems consume between 40%, 60% of the total energy in most commercial buildings. So, but they also state that by improving existing operating conditions only, we can see an important reduction in energy consumption. And this is without replacing or upgrading any equipment at all. So when you evaluate operating performance and thinking about potential options, understand the requirement first. For example, sometimes improvements can be made considering a differential water temperature set point. And by different, I'm talking about a higher temperature set point, provided that the systems, of course, allows us to accept a temperature modification. A system that was designed for 42-degree water, chilled water, but really and truly does not require 42. Instead, we can analyze how the system would perform if the set point temperature is increased from 42 to 43 or even 44 degrees. So that's a potential evaluation that we can determine right there. Another point to concentrate on is the condenser water loop and every component associated in this loop. For water cooled chillers, the cooling towers, the fans, water pumps. Maybe we can determine, we can find an opportunity to reduce the flow in the condenser, which equates to a higher condenser water delta T. Sometimes, and depending on the equipment type and the application, this results in energy savings, but it's not always the case. You cannot assume or determine that by implementing a reduction in flow, we can automatically save energy, because that is not always the case. We must evaluate the system and make that determination. Chillers, for instance, refrigerant charge. Equipments are very sensitive concerning refrigerant charge. And depending on the compressor type, one is more sensitive than the other. Keeping the controls properly calibrated and adjusted. Centrifugal chillers, capacity control and speed control for variable speed compressors. Surge prevention algorithms are critical to make sure that the compressor operates near to the surge line to maximize its efficiency. And this is valid for both constant speed and variable speed, but it's extremely critical or important on variable speed chillers or compressors, which nowadays are very, very, very common. The question always must be how far my equipment and my system are operating from design. For cooling towers, in addition to ensure that water is being distributed correctly, water treatment, etc., evaluate the option about tower fan control or fan optimization. That's another terminology for that. Always evaluate the option. Don't assume that by installing BFDs on the cooling tower, you will automatically save energy. You might, but probably not as much as you expect. For air handling units, as far as air handling units, again, know the temperature differential that the coils were selected for. We all know that, new rules or guidelines are in place concerning indoor air quality, IAQ, in which one area to consider for retrofit is air filters, and basically is to consider increasing the MERV rate to 13 or even 14. We all know that MERV 8 is the fundamental one, is the basic one, especially for residential, but for some commercial applications, I've seen a lot of MERV 8. So to increase from MERV 8 to 13 or even 14, this of course brings an additional static pressure that we must evaluate. Some equipments, RTUs, rooftop units, some air handling units are able to handle the extra pressure, but quite frankly, others cannot. So we must evaluate and make sure that the fan and the motor that we have can handle the extra static pressure. Finally, the control systems. The goal for any chiller plant is to meet the building load. We all know that. The control system plays such important role in the optimization process, but probably more importantly is the operator who is in control of the controls. So if the operators are not instructed about how the system and control should work, the system will operate in manual mode for the most part. And this is simply because the operators don't know or don't understand how the controls are supposed to operate. Any control system should have the ability to provide data and to the operators or the users and turn this data into actionable items. The key with this is to actively show how the system is operating and obviously if it's operating correctly. I want to bring this example just to identify key points when you probably study or analyze selection from your manufacturer for your particular equipment. Look at these two selections for 300-ton centrifugal chillers, commercial building, single stage compressor, constant speed, meaning no BFD. Two load line selections. One at the top is one selection. The chart at the bottom is another selection. The one at the top, it follows ARI load line and dropping the condenser water temperature as the load decreases. And the load line selection at the bottom is for the same equipment and configuration, but running at constant entering condenser water temperature. The rows in yellow, so I can capture your attention, indicate the corresponding efficiency of this unit at different capacities or load points and the entering condenser water temperature. Look at the impact in efficiency at partial loads like 80, 70, and 60%. Look at the values in kW per ton at 70, 80, 70, and 60%, and compare the efficiency values, these efficiency values in kW per ton between the upper chart and the lower chart. By taking a snapshot or a picture of this chiller and assuming that, let's assume for a minute that the chiller would run at 70% capacity, roughly 40% of the time, following what ARI says, the difference in energy consumption would be 22% in a year if it runs under the AHRI load line, meaning having condenser water relief, instead of running at constant entering condenser water temperature. And this is assuming 12 cents per kilowatt hour. I know that in some states here in the US and some other countries around the globe, electricity is cheap, but in some others, electricity is very expensive. So I assume 12 cents per kW hour and 3,500 hours, which is equivalent to 40% of the total hours in a year. If you crunch the numbers using the values at 60% capacity, the difference is even higher, which is, I come up with 30% difference in savings between running a chiller at the entering condenser water temperature of 74.3 Fahrenheit versus 85 degree Fahrenheit. And of course, we all know that, throughout the year, chiller operates at different capacity points, which, indicates basically a load profile. So the system efficiency, or SPLV, in this case, will be the weighted average of these conditions. At the end of the day, what you will have to customize your own values for a better calculation for your specific, systems or application. But I wanted to give you a general example. So the last topic, retrofit areas of implementation. As you can see here, these are the potential benefits. All these benefits are obtained after retrofits. One key element in any type of system, regardless the application, configuration, or type, is maintenance. Maintenance is a key, and prognostics is even more important. As part of any retrofit or optimization analysis, consider remote monitoring and diagnostics because it increases the value proposition or engineering value in your project. Every time that we implement retrofits, the system is optimized, the life of the equipment is extended, and the equipment value is increased simply because the way in which now this piece of equipment performs. And the net result is that it is more efficient, which is what we're looking for. The whole idea behind the analysis of the system by using or implementing the SPLV, the system part load value, is to find areas to reduce operating costs and to increase or maximize the efficiency. Sometimes redundancy is part of the optimization, depending on the system requirements and obviously on budget available. From the operational standpoint, we need to consider three important factors to achieve energy balance and maximize this efficiency. Number one, we must eliminate the energy that is not used. A perfect example of this energy that is not used is a throttling valve, like a triple duty valve on a pump. As an example, which I've seen in many mechanical rooms, when a BFD is used to control the pump, and I still see this triple duty valve installed in the living piping. But think about this: there is no reason for the waste and cost of a triple duty valve, even if active VPF or variable primary flow is not being implemented. The speed of the pump can be adjusted to control the flow and have a greater savings over the triple duty valve. Second point to consider is component sequencing and stability, whether it's stacking or controlling chillers with a BFD or controlling the fans in cooling towers. Regardless the case, proper sequencing is part of optimization. For example, one chiller can operate at 100% capacity or full speed if the chiller is a BFD or has a BFD, but two units can share the load at 50% capacity or 50% speed. Now, this is valid if and only if the system is designed to accept these operating conditions. Not always two chillers or partial load are more beneficial than one chiller at 100%. Every site or system is different. I cannot assume that this way running my plant or my system in this way will give me 100% of my savings just because some other systems operate the same. So we will be better off by understanding each system individually and apply the modifications that the system really requires. Really, evaluation and understanding of the system is a must and it's not an option. And the last point to consider, remember that I mentioned three key parameters, is proper capacity control. This is more to understand the limits of every equipment. As an example, case of centrifugal compressor, in the case of this centrifugal compressors or even screw compressors, is lift or head. Sometimes those settings for capacity control are completely off and way off in reality. And the consequence is that we have a chiller that is not performing correctly, is wasting energy and causing, for the most time, temperature fluctuations. For retrofits, this is an example that we're going to use. We're going to use centrifugal chillers, great machines to play with. Major compressor overhaul. Now with synthetic oil, the tendency is to use the oil analysis results to determine when the mechanical intervention is required based on what and which type of particles in suspension are found in the analysis. Vibration analysis is also used in conjunction with oil analysis to determine the health of the compressor. But if we take this in consideration, this is a great time to consider and to evaluate operating conditions, to perhaps review history logs and find weak points. And this is the opportunity when we can sit down with the customer and discuss about existing capacity of the building and certainly by all means operating conditions. Maybe the capacity of the building was increased over the years or is about to. So we have the opportunity to evaluate the aero components, the aerodynamic components for this compressor and see if by modifying some of them, the unit improves the efficiency and performance. Another thing that we can consider at this point in time is the addition of a BFD for a better partial load efficiency. Look at the condenser water conditions, temperatures, flow rate. We have opportunities to increase the heat transfer capability by replacing the tubes. Maybe we find opportunity to control the cooling tower fan with a BFD, but always check the limits. And when I talk about limits, keep the following in mind. For cooling towers, confirm what is the minimum fan speed and the minimum flow rate to prevent poor distribution of water and poor heat transfer. For chillers and pumps, confirm minimum and maximum flow rates, minimum requirements at low loads, specifically at low loads, to make sure that the unit is stable. This is key. Understanding what is the minimum requirement at low loads will guarantee a stability of the unit, especially at partial load, but more important at low loads. Understanding these limitations and operating conditions will help you to determine whether a BFD is a good addition or upgrade for the equipment, whether it's a compressor, a fan, or a water pump. Oil reclaim. For oil reclaim in some units, it's important to improve the oil return system or piping in order to reduce the amount of oil residing in the cooler, which basically affects the heat transfer rate, especially at partial load, in which the oil returning, the oil velocity returning from the cooler to the oil sump is very low. So check with the manufacturer because some of them have modifications in place to improve this oil return system. Refrigerant conversions. For refrigerant conversions, sometimes engineers take advantage of these conversions and evaluate aerodynamic components specifically for centrifugal compressors. For other compressors, you don't have such an option, but for centrifugal compressors, we can basically do a lot of things. Um, Aerodynamic components are evaluated to increase capacity or better performance, a partial load, or maybe both. Once again, adding or considering BFD is a great addition. But now, since refrigerant conversion is usually followed by capacity loss, check and confirm motor limitations about mostly output power and rated load amps or RLA. But again, it all depends on what is the refrigerant that we have and what is the refrigerant that we're migrating into. For example, I conduct a lot of analysis and energy analysis for existing equipment operating with R12. The customer wants to retrofit or convert the unit from R12 to 134A. When we switch 12 to 134A, the polytropic head is increased, and as a result, the brake horsepower is increased, and the net result is the overall compressor efficiency decreases. So the main idea here with all this is to reduce the compressor energy and improve the way heat is being rejected to the atmosphere through the condenser. The result is an increase in the net refrigerant effect and efficiency, and this is basically what the cartoon states in this slide. One thing that is important to understand at this point, and basically from what I've said, is that you don't necessarily need a BFD in every single motor in the chiller plant to have an efficient system. That's a misconception that in order to save energy, you just throw BFDs in every single motor and we're going to expect 50% energy savings. That is not the case. The first and most important factor in a chiller plant is balance. The system efficiency is greatly influenced by the design conditions. And to say the same thing differently, if the design conditions are properly balanced, there is much less excess energy to be controlled out of the system. And understanding this is important. This is kind of a recap of the presentation. This is actually my last slide. So for every retrofit, we should apply this cycle, starting by knowing and understanding the design and operating conditions. There are some questions to really tackle at this point. For instance, what are the constraints of the original design? And is the system working as intended? Evaluate the existing configurations to see if it's applicable to what is desired to have. In other words, let's say two chillers in parallel and one of them is smaller. This type of application or configuration where two different sizes of chillers are in place, VPF or variable primary flow will be hard to implement or to apply due to the different limitations between the units. But always contact the chiller, the pumps, and the cooling tower manufacturer and ask for this limitation, ask for these limits. Sometimes in a chiller plant, let's say 3 constant speed centrifugal chillers, we can apply diversity and install BFD in 2 of them, in 2 chillers, while keeping another one, the third chiller at constant speed. So the main idea with this is to handle the peak load with a constant speed chiller and the partial load with the ones with BFDs. And this is, of course, this is just an example of many variations that we can have in the field. But once again, all boils down to existing conditions and requirements. Applying BPF or variable primary flow on the condenser's loop requires to know the limits of the chiller. The main one is water velocity at 100%. You might remember a few slides back, I mentioned some of the requirements for this type of system, BPF, from the controls and logic standpoint, which is reducing the load and flow rate linearly. You know what happens when the flow is reduced and the cross-sectional area of the pipe is constant? The velocity is reduced. This is a simple, basic principle of fluid mechanics. If the water velocity is reduced and the minimum acceptable velocity is 3 feet per second, that means that we must know the water velocity when the unit is at 100% because it is our starting point. If the water velocity is already low, let's say 5 feet per second at 100%, and I've seen this many cases, we might not have enough room to apply this concept at low loads. Maybe we can just reduce the flow until 75% or even 80%, which is even worse, but not further than that. For pumps, rebuilding pumps sometimes impeller trimming is the key in order to match not only volumetric flow, but also total head. But remember, the number one condition is to eliminate the energy being wasted. Remember the example that I mentioned a couple of minutes ago about the triple duty valve on a installing a pump that is being controlled by a BFD. And finally, once again, cooling towers. I guess that by now we all know that we have several options to consider when we analyze the condenser side, tower fan control for optimization, temperature adjustment, etc. But always check the limitations with the manufacturer, which is the main takeaway, not only from this slide, but also from the complete presentation. So I guess that for this, I complete my presentation at this point. I hope that you have enjoyed and got the basic principles and ideas about chiller water plants optimization and how we should approach these opportunities. There is not really a silver bullet. Every system, every plant is different. And the idea is to evaluate each one individually from a system standpoint and try to determine and evaluate each opportunity that we can potentially apply. I would be more than happy to assist you in any way. If you would like to connect with me, I'm on LinkedIn, so we can take it from there. So with that, Amy, I think that is a good time to move to the Q&A session.
Yes, thank you very much for that excellent presentation. Just a reminder, if you do have questions based on the presentation or you need clarification on any points, please feel free to use the Q&A panel at the bottom of your screen. You can just hit that and then it'll open up a text box. You can type in your question. So the first question is, you said 3% per degree Fahrenheit for cooling towers or condenser water. What about leaving chilled water? I've been told that it's worth 3% per degree of SST. Can you clarify or comment on that?
Yeah, that's a great question. I think that the message that I wanted to convey to the attendees is that when you increase the entering condenser water temperature, in the case, of course, of a water-cooled chiller, the power consumption increases approximately by 3%. In some equipments might increase by slightly 2%, in some others 1.5. It depends, but I've seen in most cases that a dramatic 3% of power consumption is increased by every degree of entering condenser water temperature. Now, from the chill water side, I guess that you can increase the living chill water temperature as the equipment is able to. In other words, if for some reason the application requires a higher chill water temperature, let's say that the chiller originally was selected 44, and for some reason we wanted to run it at 47 degrees, make sure that you contact the manufacturer and ask him to reselect the equipment for 47 degrees. Of course, from a very general perspective or view, you might be thinking that, hey, I have an opportunity to save some power, some money, because if I increase the chill water temperature from 44 to 47, that means that the lift of this piece of equipment will be, much less. And if I reduce the lift or the head, so there is an opportunity to reduce the power consumption. But again, the question is, how are you going to handle the condenser side? And it all depends whether it is a water-cooled chiller or our air-cooled chiller. Because yes, evaluating one side might bring you some savings, but don't forget that that chiller is also tight, is married with whatever happens to the outside. So I would suggest at this point that consult with your manufacturer, and if you have some sort of idea that the chiller might perform even better at a higher temperature, make sure that the manufacturer reselects your equipment at a higher temperature and see how or what the benefits are, basically.
Perfect. Thank you. Our next question is from an attendee who's just looking for your input. He's got two chilled water plants completely separated, each serving one building, would connecting both chilled water plant rooms through a plate heat exchanger lead to energy savings in part load conditions?
Well, that's a great question. I remember a couple of years ago, I was involved in a similar project in the southeast. Two different individual and completely independent mechanical rooms, and the objective was to combine these two and provide even more cooling or more capacity to a set of buildings, basically. I remember that at the time we used a buffer tank, and of course that was, we had an office space, and we have the ability to add a buffer tank big enough to handle all this thermal inertia in the system, and we were able to to meet the objective of increasing capacity, increasing flow rate. Heat plate frame plate heat exchangers might be the solution, but it all boils down to, my guess, to look at the system individually. What do we have in one system? What do we have in the other one? Let's see what is the best way to combine these two. I would say that the plate heat exchanger might help, but it all boils down to crunch the number and see what is the most beneficial one.
Perfect. Um, do you find non-chemical water treatment to be more efficient and easier to manage than traditional water treatment?
Well, you know, by carrier rules, we must apply chemicals to the water, to the condenser water, just to keep certain ppms. Well, not only ppms, but also the pH, the acidity, and some other chemical constraints that we usually deal with in open circuits, in open loops. But I've heard and I've seen and I've used some other products, electrical conductivity. It's a system that you apply some flanges on the on the pipe, I'm sorry, and they basically conglomerate all the particles in suspension, so it reduces the amount of ppm. So in that way, it all depends. I mean, if the site, if the issue in the site is a high ppm, high calcium, that probably would solve the problem. But I've seen some others that particles in suspension is not really the issue, but actually the pH, uh, high pH. So it depends. We must evaluate, the system and consider the different, portfolio of options that we have out there to determine which one work best for this particular application.
Yeah, that makes sense. Another question, of the R12 chiller retrofits that you had mentioned, were they successful? What replacement refrigerant did you use and what was the overall loss in efficiency?
Yeah, great question. I actually oversee a group of people that conduct retrofits specifically on centrifugal chillers, and also a small amount on the screw chillers. But they're all, they were all yield positive results. Again, when we migrate or convert R12 units to 134A, which is the current option to for refrigerant conversion. And I know that we have the 513A. That's another refrigerant that it is currently available, and it's supposed to replace or be an equivalent of 134A. But when you compare these two, definitely the 134A still provides or brings some benefits, specifically from the energy consumption standpoint. But what happens with refrigerant conversion, and specifically for centrifugal chillers, is that we have the ability to increase the impeller size. We can modify the diffuser, and we can increase or decrease the number of pipes in the diffuser just to accommodate the head or the static pressure of the refrigerant leaving the compressor, which is the one that is going to help us to for the condensation of the refrigerant. We can also replace the shroud, which is this little cone at the suction of the impeller that either increases or decreases the capacity. So we have all these combinations. One of the things that we implement while we're undertaking this type of analysis is equipment optimization. And equipment optimization is basically out of this many sizes of diffuser, and I'm taking the diffuser as an example, we must determine the one that it has the lowest initial cost, meaning less investment from the consumer standpoint, but it brings what we need in terms of static pressure and efficiency of the compressor. So we put all this, imagine that we're putting all this in a blender, and the final result is this combination of impeller, diffuser, shroud, etc., that will bring not only the capacity but also the efficiency that the customer is looking for.
Perfect. We have another attendee who works in a museum environment, so humidity control is very important. They said as the chilled water leaving temperature rising and energy savings are realized, the humidity control tends to suffer. Can you speak to that, or what you see to reconcile that?
No, absolutely. You might remember that I mentioned it probably, I don't know, 5, 10 times, that understanding the system requirements is a must. I do understand, like I mentioned, probably was the first or second question, that increasing the living chill water temperature might bring some savings opportunities, but in this type of application in a museum, I'm actually affecting, the end result, which is keeping all my pictures, my frames, and everything inside that museum, all these figures or whatever we have at a certain relative humidity and a certain temperature. So we must evaluate really what is really what we need to do. I mean, do we want to save maybe 5-7% in energy consumptions because I'm increasing the chill water temperature, and I'm willing to waste or to lose my, I'm going to call this production in my museum, which are all my pictures, my frames. That's the question that we need to that we must ask. And I don't think that in a museum we have much room to play, because those conditions are really imperative to keep in control, meaning relative humidity and temperature. Relative humidity mostly rather than temperature. It's a key in a museum or any other kind of an antique application, if you will.
Perfect. That makes sense. And can you just talk about what is the recommended sequence for operations for a multi-chiller plant setup? He said example would be 2 60-ton machines and 1 200-ton machine on a pumping setup.
Yeah. Unfortunately, Amy, that's a very long answer, and I would love to follow up with the attendee or the engineer who asked that question. So I will definitely get back to him with some sort of ideas, depending on the system. But again, depending on the system type, whether it is parallel configuration, series, we have different control schemes that we can apply to control the chillers and the pumps in the most reliable and best way.
Perfect. And then just a few questions on Carrier product specific. How does Carrier address oil fouling as applicable to thermal to heat transfer? Do you have an optimization solution that can permanently coat internal coils or metals?
Let me see if I understand. Is the question asking if there is any specific oil type to increase heat transfer effect?
Yeah, so do you have an optimization solution that can permanently coat coils and internal metals? I'm not sure. We can move along to that. Ed, you can follow up with that attendee if
Absolutely, yes.
Yeah.
I just want to make sure that I understand.
Sure. No, we understand. So we are at the top of the hour, so we're just going to wrap up for today. Ed, thank you again for a great presentation. Is there any final words you'd like to leave with the audience? Any final recommendations?
No. Like I said before, I'm on LinkedIn. I will be more than happy to connect with all the attendees and be able to, to the best of my abilities. Of course, I don't know everything in the world, but I will definitely do my best in answer any questions that they might have.
Wonderful. Thank you again. Just a reminder, you will get a copy of today's presentation. So check your emails, and you'll also be getting a link to take your quick assessment so you can earn your certification for joining us for today's event. Thank you again to Carrier and to Ed for presenting the information today. Have a wonderful day, and we'll see you again soon for a future event. Bye-bye.
Thank you, Amy.